Everybody, so let's get started on our next session. Our first speaker is Mohammed Amin. So let's get going.
Good afternoon. I would like to thank the organizers of this conference, especially Nishimori-san, for inviting me to this conference. I know those of you who came from North America are extremely jet lagged like me, so I hope I don't fall asleep during my own presentation, as Seth suggested. But if you guys feel you want to sleep, please feel free to close your eyes. I don't think I need to motivate my title. If you were not interested in this title, you wouldn't be sitting here. So I would just jump to my first slide. These are a few statements I picked from some recent papers. If you look at this, you can see some words are repeated, like, efficient, and scale polynomially. And if you take these statements literally, especially the last one, that quantum Monte Carlo is efficient and polynomial, scales polynomially, this means P equals NP, without the question mark at all. And the authors of those papers are very knowledgeable and smart. I'm pretty sure that's not what they mean. So the first thing I want to mention is what do they mean, and what is efficient, what is scalable, what scales polynomial, what doesn't. Or in other words, what is fact, what is myth. So fact number one, I think all of us agree on this fact, that quantum Monte Carlo can simulate equilibrium statistics of a stochastic Hamiltonian that doesn't have sign problem. We all agree on that. Fact number two, it's a little bit less obvious. At non-zero temperature, the number of variables that is required to do fact number one scales polynomially with size. I say it is likely because I haven't seen any mathematical proof. Has anybody seen any mathematical proof on that? But intuitively, yeah, you have seen? Okay, I'm happy that Elizabeth is here to help. But I'm a very intuitive person. My intuition is quantum Monte Carlo gives you, solves the problem by adding an extra dimension. And if temperature is fixed, the size of the extra dimension is fixed. Therefore, the volume of your computation just scales polynomially with the number of variables. Therefore, it is reasonable to assume that the number of variables required to do this kind of calculation is scaled polynomially. And I believe that is what polynomial scaling meant by those papers. But what is also well accepted, I think, is that the time is not polynomial. Time is exponential. If the time was polynomial, then P equals NP, and then we are in trouble. So, but none of these talk about the dynamics of quantum Monte Carlo compared to dynamics of a real hardware quantum annealer. And I want to mention the myth, which I have heard a lot, that quantum Monte Carlo can simulate dynamics of quantum annealing. And this I want to show that is not true. But indeed, there have been several papers already in literature. Stephen Jordan is here, and he's going to talk about his recent result on this. There have been several papers that have shown that quantum Monte Carlo does not simulate the dynamics of real quantum annealer. But one may argue that, okay, these papers have considered very contrived, unrealistic problem, maybe in realistic problems that you can implement on a hardware. This does not hold. Okay, so during the last year, I think two very interesting papers appeared by Google guys and Matthias Troyer. The first one was this one. And the significance of these papers was that they showed really they compared dynamics of quantum Monte Carlo with the dynamics of a quantum annealing when quantum annealer does incoherent tunneling. The first one was at zero temperature, and the second one was at finite temperature. And both of them came to the same conclusion, that dynamics seems similar. So I want to tell you what these papers show first. They look at a fully connected ferromagnetic system. And if it is fully connected ferromagnetic problem, there are two ground states at zero bias. There are two ground states, all up, all down. I denote them by U and D. So it's clear what I mean. And if there's transverse field available, then you will have tunneling between them. I denote tunneling amplitude by G. Now, what these guys do, they go through some techniques, large spin model, which is Vadim's specialty, and WKB approximation, which is a usual technique for this kind of thing. And what they show at the end is that if you look at incoherent tunneling is scaled as gap as G squared. I call it gap because when you look at the spectrum, this is a real gap. But quantum Monte Carlo also scales as G squared. So therefore, there shouldn't be any scaling advantage. And if you want to extrapolate this result to other problems and everything, then you would say, okay, there's no scaling advantage of quantum Monte Carlo because the tunneling events eventually scale the same. But does that mean that quantum Monte Carlo can simulate quantum annealing? And my answer is no, so I want to convince you that the answer is no. I have two arguments. First of all is this paper looks at only one problem, which is uniform ferromagnet. And this problem doesn't have any frustration. And I want to show you that frustration can change this result significantly. The other answer is these papers look at incoherent tunneling. And I don't believe incoherent tunneling is the main resource of quantum annealing. The quantum annealing is not different from other quantum computation algorithms in the sense that the resource should come from entanglement and larger scale superposition. But in a different way that I will talk about at the end. Okay, let me start from this. So when we saw this Google paper, it actually inspired us to dig down to see what's going on. And I personally learned a lot during this process. And it led to this paper I published with Evgeny from D-Wave. But to explain this, I have to explain a couple of things. The first thing, I want to explain what quantum Monte Carlo is. I remember last year, Peter Love was in the audience. He gave a talk, and he said, if you don't want to hear about solitons, please make non-stochastic quantum Hamiltonians. So I think there is a way to talk about quantum Monte Carlo without solitons. So I will not talk about solitons. Don't worry about it. The simplest picture that you can think of quantum Monte Carlo is the following. As I mentioned, the quantum Monte Carlo is about equilibrium statistics. And we know that equilibrium distribution is completely described by a function called partition function. And for quantum case, partition function is defined by trace of e to the minus beta h, where h is the Hamiltonian of the problem. Now I can just do a trick. I can divide this h by m, which m is an integer, and then multiply m of them, give you the same result. Then I can insert these identity operators, which is sum over all s's, between them. And you can easily see that you get a sequence of states, S1, S2, to Sm, and go back to S1. So the sequence of states that would make a loop in a hypercube. So this is a hypercube. You will see this a lot in my presentation. And this sequence of states represents a loop in a hypercube, but the loop is directional. So the direction of the loop matters in this calculation. Now you can write your partition function in terms of e to the minus free energy of the loops. So quantum Monte Carlo give you a recipe how to calculate this free energy. Don't worry about it. So now you can write Monte Carlo algorithms based on these loops instead of based on states. You can deform the loop and then ask whether I can accept this or not accept it based on the free energy of the loop. instead of energy of states. And that's quantum Monte Carlo is. Now, that was the first thing. The second thing is, how is, in the simple language, partition function related to tunneling? So because in the result I showed from paper, the paper I showed from Google, guys, you saw that everything depends on gap, and gap is squared, or tunneling is squared. You can simply, very simple language, see how partition function depends on tunneling. Imagine, so let's go back to the example I showed you before. You have two states, up and down, ground state, you have tunneling. If you calculate when this G is much smaller than the energy gap between these two states and the upper state, you can approximately write ground state and excited state as E0 minus G, E0 plus G. E0 is the ground state before tunneling. And then to a good approximation at low temperatures, partition function depends on these two states. You get e to the minus beta E0 minus G and plus G. You can expand, and the first term that you get that is something proportional to G squared. And this is exactly G squared that appears in Google paper. So, and you will see how it shows up. Because of importance of this term, because we have introduced a name for it, we call it boundary partition function. And you'll see later why we call it boundary partition function. But for now, let's call it boundary partition function. But this is based on just Taylor expansion. But quantum Monte Carlo is about loops. So I want to express the same thing in terms of loops. It turns out that this boundary partition function that we discussed is just sum over all loops that have two fixed points at these two states and make only one term. If I make more than one, if I make two terms, then I will get something proportional to gap to the power of 4. Gap squared gives you one term. If you want to calculate tunneling amplitude, you have to sum over all paths from up to down. Now you can also convince yourself that every loop consists of two paths, going up and one going down. And it turns out, by using perturbation theory, that the equations are very similar. And actually, you can actually prove this using perturbation, and we also prove it beyond perturbation. So this is a very general result. It still holds when G is small, but it's non-perturbative. Very general result. That this partition function, boundary partition function, defined this way, is proportional to gap squared. Now, why does it matter? Let's consider as the simplest possible tunneling, which is one-dimensional tunneling. So this blue line represents the states that have lowest energy along the path of tunneling. And as every state that is outside this blue line has higher energy. So I assume that there are other states as well. Now, if I want to write all terms that contribute to boundary partition function, I will find that the lowest term, energy term, that contributes is just going along this path up and down. Everything else will have higher energy and therefore suppressed. Therefore, to a good approximation at low temperatures, this path, which goes up and down along this low energy path, is proportional to gap squared, as I mentioned, as I proved to you before, because this is the only term in boundary partition function. Therefore, the probability of getting this loop in your Monte Carlo algorithm is proportional to G squared. If instead of one path you have two paths, then you have 4 possibilities. You can have your loop extended along left leg, right leg, or going left and coming back leg. And as I mentioned at the beginning, these are directional loops. Therefore, the going clockwise and counterclockwise are different. So therefore, you have 4 possibilities. And again, these 4 possibilities are the only term that matter for boundary partition function. And because of the theorem or the proof that I mentioned, the sum of all 4 is proportional to gap squared with the coefficient that I showed you before. Now, up to this point, this is all equilibrium statistics. There's no dynamics here. So how can I relate this to dynamics? Now, let's look at a very simple example, again, one-dimensional, and ask, if I start my problem from up a state, one of the minima, how does it escape from one minimum to the other one? In classical thermal excitation, this state just moves, or this loop just moves up and goes there. But at low temperatures, because the energy in the middle is big, because at low temperature, these are highly suppressed. So what happens in quantum case, this loop stretches and then contracts. This is how escape happens. And indeed, this process does not depend on temperature. So it looks very similar to tunneling. When you decrease temperature, this is what dominates and doesn't depend on temperature. So you can say this is like how quantum Monte Carlo tunnels. You can interpret it as a tunneling. Now, if I plot this free energy, I'll see that this free energy has maximum exactly when this loop is largest. Therefore, barrier is at this point. And Kramer's law tells you that if you start from one side and you have some process that gives this local equilibrium on one side, the probability of escape is proportional to the probability of reaching the top of the barrier. And I told you the probability of reaching the top of the barrier is the probability of getting this boundary partition function. Therefore, quantum Monte Carlo escape is proportional to gap squared. That's what Google people proved. And indeed, in their case, it's inherently one-dimensional problem, although it looks like multi-dimensional problem. Now, let's generalize this to two paths, the simplest case of two paths. Now, if it is two paths, I have two possibilities. I can either, I told you have to stretch the loop in order to mimic tunneling. I can either stretch the loop along one of the paths, which is the top case, or I can stretch the loop along both paths, which is the bottom case. In the top case, then it's exactly the same as we had before. The barrier happens, the maximum free energy happens in the middle. And by the way, all the boundary partition functions happened right in the middle. So that's what we call boundary partition function. It's exactly in the middle of the left and right situation. Now, so you can see now again, the barrier happens in the middle, and then the probability of escape depends on the probability of reaching these kind of loops. But if I consider this other path, there is no way I can stretch this loop along both paths and not leaving the low energy path. I have to leave this low energy path. And these states along this path has higher energy because I'm leaving the low energy path. And if these states are penalized enough, I can completely suppress these two cases, and I get a factor of half. And these are indeed very closely related to topological obstructions that Matthew Hastings and Mike Friedman mentioned in 2013. Now, to show you that this is not a fantasy, it can happen in real life, I can give you an example. So consider a ring of qubit spins, all coupled ferromagnetically with minus J, except one bound, which is this red one, which is J minus epsilon, and it's antiferromagnetic. But antiferromagnetic coupling, but weaker than the other ones. Because it's weaker, then it is more favorable that we violate this leg than the other legs. So therefore, the ground state will be all qubits up or all qubits down. And if you want to flip all qubits from up to down, the cheapest way, the most lowest energy path will be by flipping qubits one by one from clockwise or counterclockwise. And it gives you two paths. You can see these qubits are flipped from this way or that way. And this is exactly similar to the two-path tunneling that I showed you before. And by the same argument that I had before, if all other paths are suppressed, I will get a factor of 1/2. But this doesn't scale. So if I scale this loop, this factor of 1/2 doesn't scale. So I wouldn't get anything that scales with size. But if I couple many of these loops together, this is something that Mori called it shamrock, so this is now a standard word, shamrock. And so now we have k of these loops, all of them having an antiferromagnetic coupling, and the rest are ferromagnetic, but only 3 qubits. And the middle qubit is shared between all the loops. And you can convince yourself that every loop can give you a factor of 1/2, therefore you get factor of 1/2 to the power of k, where k is the number of the loops. So now, if I scale this, I get something that the prefactor between quantum Monte Carlo, escape, and tunneling scales as a function of the number of qubits that we have. We did some numerical calculation to confirm this actually agrees. This is 15 qubit maximum, which is 7 loops. So k is 7, 2 times 7 plus 1 is 15. That's correct. The red one is 1 over, this is escape time, not rate. So now it's 1 over escape rate. The red one is 1 over g squared. That's what you predict for incoherent tunneling. The symbols are quantum Monte Carlo, number of sweeps of quantum Monte Carlo. And the dashed blue line is this line times 2 to the k, and it fits very closely to quantum Monte Carlo escape, so that therefore it confirms this kind of exponential prefactor that we predicted. So this kind of ends my first part of the talk, that even for incoherent tunneling, the argument that was shown in Google and Matthias' paper cannot be generalized to all problems. It's just specific to problems that don't have frustration. And indeed, all interesting problems have frustration. So this is more generic than you expect than just unfrustrated tunneling. But now I want to get to the main part of my presentation. I don't think incoherent tunneling is the main resource of quantum annealing. What is the resource of quantum annealing then? If you ask any gate model people who are, I think a lot of people are familiar with gate model, what is the main resource for gate model? I think people will say quantum parallelism. So quantum parallelism means you have a wave function that is superposition of a state, and then you apply a gate, and all states go through the gate in parallel. In quantum annealing, we don't have gates, and we don't have pure state. Usually we have mixed state. So this just taking this quantum parallelism, quantum annealing is kind of hard. I want to actually introduce a new terminology here again. I want to say quantum dimensionality reduction is what is the main resource of quantum annealing. Before getting to this quantum dimensionality reduction, I want to say what is dimensionality reduction. If you have dimensionality reduction is a very powerful technique in data analysis. If you have a data that is given to you in multidimensional space, in this case it is three-dimensional. It's a very simple case, x, y, z. If you look at this data by your eyes, you immediately realize that this is actually one-dimensional data. It's not three-dimensional data. And if I could detect this particular dimension, which is a uniform linear sum of the other 3 dimensions, then I could have a much more compact description of data. And if I want to do any analysis, any computation on this data, I could use this lower dimensionality to do computation much faster. Now, how is it related to quantum annealing? We don't have the data. This is not data analysis. In quantum annealing, we have solution space that's exponentially extended. And solution space in classical system is like hypercube. You have in 3 qubits, 3 bits, you have a cube, and this is 7-bit hypercube that I showed you before. And you immediately know that this hypercube scales like exponentially. The hypercube grows very fast. But very similar to the dimensional reduction argument, which you had a linear combination of all the axes, now you can have linear combination of all these axes. And every linear combination gives you some quantum state. And therefore, you can define a lower dimensionality state to define your computation. Indeed, adiabatic quantum computation is the lowest dimensional reduction argument. So you confine your computation between two states, and then all of your argument depends on how your computation happens between these two states, which depends on the gap between two states, and you ignore the rest. A better example is a very nice paper by Rolando Sama. And in this paper, they consider glued tree problem, which was introduced by Andrew Child, who they considered this problem for quantum walk and showed exponential speed of quantum walk compared to all classical algorithms. But Ronaldo considered it in kind of quantum annealing concept. Now, these red dots are states. These are not qubits. These are states. So you have one state, and you want to go from this state to the other state, and you have these, and these are paths. So this is very similar to the situation I described. You have paths of tunneling. Now, if I follow this incoherent tunneling argument, I can calculate tunneling amplitude between these two through all these paths. I get some gap, and I can compute the topological barrier that I described. And all I find is I can get some polynomial speed up this way based on incoherent tunneling. However, if I allow the system to form extended eigenstates, I will get, and I confine myself into two lowest states. Again, this is dimensional reduction. Then, if I want to do adiabatic quantum computation, I will fail. These gaps become exponentially small. But if I allow the system to make transition, non-adiabatic transition, to the excited state, and then non-adiabatic transition back, I can get exponential speed up. And you don't need non-adiabatic. You can also have thermal transition, and it doesn't change. As long as coupling to environment does not kill these eigenstates, the result will be the same. So having access to these eigenstates, which are extended eigenstates, and having access to this path can give you exponential speed up. So that's why I'm saying the real power of quantum annealing comes from having access to these extended eigenstates. And the evolution can be incoherent. You don't need coherence between these eigenstates for this to work. All you need is having access to these eigenstates. Now, this is again for a kind of optimization concept. I want to generalize this to sampling. Now, another important point is this exponential speed up cannot be achieved by quantum Monte Carlo. So this is a very good example that quantum Monte Carlo is exponentially slower than a quantum annealing that has access to these eigenstates. Now, I want to generalize this to the sampling. Now, imagine you want to do a Boltzmann sampling. All you need to do in this Monte Carlo algorithm is to start your algorithm from some random point and then have random walk, and then have some acceptance rule that gives you equilibrium at the end. But if your distribution that you care about is exponentially extended and it's complex enough, then you have to wait exponentially long time to wait for this random walk to reach all the states or cover the whole space. Now, if I give you a bunch of states that each of them are exponentially extended, but the number of them is much smaller. I don't want to talk about polynomial versus exponential. I don't want to get caught by these complexity theories. But suppose you have a smaller number of these, but each of them is exponentially extended. If I want to generate the Boltzmann distribution, I need to do a random walk here. And the number of steps that I need to do to cover the whole space is n, which is the number of these states, not big N, which is the number of classical states. So I can gain a lot by introducing these eigenstates. So these now can be eigenstates, and introducing these transitions between the eigenstates. A quantum machine doesn't need to simulate these eigenstates. A quantum machine has these eigenstates available to it. Whereas an algorithm like Quantum Monte Carlo has to simulate these eigenstates. So that's where the advantage comes from. If you look at how a quantum annealer, open quantum annealer like D-Wave work, the way it works is you have coupling to the environment and you have transitions between ground state and many states. This height is temperature. As you anneal, you get mixing between a lot of states, and then the transition rate becomes slower and slower. That's why the arrows become narrower, and then you get freeze out at some point. So this transition up and down is similar to what I mentioned before. Gives you equilibration in this eigenstate. But what you need to show is these states also are extended, and they're not always extended. Now, suppose I have a landscape like that. This is a classical landscape. Usually we represent this way, one dimension, but it's really in a hybrid cube. Now, people who are familiar with many-body localization, they tell you that the eigenstates of this system, when you have transverse field, are separated into two parts. Some of them are localized, and some of them are extended. And the boundary between these two extended and localized is called mobility edge. I hope Vadim was here. He's fascinated with mobility edge and many-body localization and stuff like that. Now, depending where temperature lies, the dynamics will be different. If temperature is below mobility edge, then there is no way to go from this left valley to the right valley without incoherent tunneling. So if the temperature is below mobility edge, incoherent tunneling is the only way that works for you. But that happens late in the anneal. If you go a little bit earlier in the anneal, the energy scale goes down, the transverse field goes up. And the mobility edge becomes lower than temperature. Now, the cheapest way is not incoherent tunneling. The cheapest way is to excite the system and go through these extended eigenstates. And I would call it transport via extended state, which is very similar to Ronaldo Soma's paper. So you go transport through the extended eigenstates. When you anneal the problem, usually you pass these regions very quickly, and you may not see the power of them. But if you stop and let the system equilibrate, the equilibration rate depends on this dynamics about among these eigenstates, and you would be able to see the difference between classical and quantum Monte Carlo and quantum annealing through the equilibration rate, through dynamics. You shouldn't look at the statistics. Statistics at the end are the same. If you want to compare the two systems through just ground state probability, you wouldn't get anything because they're the same. You should really measure the dynamics. And so in order to do that, you have to be able to measure the dynamics, and you have to do some tricks which you cannot do with current annealer that I have, but I'm happy Trevor discussed this morning. We are allowing other features that allow this kind of measurement to be done. Okay, so now let me go faster. So what happens during annealing is at the beginning you get very fast equilibration, you get quasi-static behavior. The problem freezes and then becomes frozen at the end. And the interesting region that you will see a speed up, I believe, is around this region, that you will still have equilibration and you have extended eigenstate, and you get this power of annealing due to the extended eigenstate. This is a measurement a colleague at D-Wave did. This is a measurement of freezing for 128 qubit problems. And you see the freezing is very, very wide. And in order to get a good Boltzmann distribution, you need the freezing be very narrow at one point. So if you just anneal and hope you get quantum Boltzmann distribution, you wouldn't get it because this is very large, wide freezing. However, Trevor talked about this feature. I don't talk about it, like annealing with quench and annealing with pause. What happens is if you pause, it will allow the system to equilibrate longer, and this pushes this end. If you quench, it will push the other end because the qubit will freeze earlier. And this is the result you will get. So with the quench that we have available, 1 microsecond, you can push this a little bit, not too much. And Emil paused 100 microseconds at this particular point. You see this side is also pushed. And we get a little bit better situation. But if you really, really want to get Boltzmann distribution at this point, we need a quench that push this all the way to this point. And we need much faster quench. And once we get this much faster quench, we can talk about dynamics and compare quantum Monte Carlo with quantum annealing. I just want to mention, I want to show you one preliminary experimental result. We want to compare, again, dynamics, equilibration dynamics of our hardware with quantum Monte Carlo. We introduced this measure of error, which is just looking at the expectation values of this correlation between exact and the hardware. And this is the result we get. If we quench early, so you don't see this much. The red line is hardware, the black line is quantum Monte Carlo, and the lower is the better. So you see quantum Monte Carlo actually beats its hardware very early. The reason is we quench, but during the quench, dynamics happens and this screws up the distribution. So the real distribution of the hardware is much below that, but this is the distribution you get is on freezing during the quench. But if we quench later and later, we can see the effects of quench, and we can see that the quantum Monte Carlo cannot beat hardware anymore. This is how, you don't see these numbers, this is 500,000 sweeps. So with 500,000 sweeps, quantum Monte Carlo cannot get any closer to what the hardware is. And this is 128 qubit, this is 500 qubit, the gap, it becomes even bigger. And this is not just rare events, we have seen it many, many times. So this is a direction that we want to see, look for quantum advantage, that the quantum advantage in the real dynamics, not in distribution only. So I can summarize, I hope I showed the quantum Monte Carlo cannot simulate quantum annealing. You will hear more talks from Stephen Jordan and others. And so I hope I convinced you that there is another application of quantum annealing, not just optimization, but sampling from quantum Boltzmann distribution, and it has some application, which is quantum Boltzmann machine. I was happy to see many posters on this topic. And finally, we have some early experimental results. What I showed is just very, very preliminary. If you want to see more, please listen to Richard Harris and Jack Raymond's talk tomorrow. Thank you.
So you spoke a lot about incoherent quantum tunneling. Could you comment, but you didn't really say anything about coherent quantum tunneling. Could you maybe comment on why and possibly maybe what role coherent quantum tunneling could have if you had perhaps a more coherent quantum annealing?
Yeah, the coherent quantum tunneling, you may think of having some oscillation, but you don't get oscillation in this case. So what matters here is you have extended eigenstates. If you could do start somewhere and do very fast evolution, you would see oscillations. But that's not what we do here. You would see oscillations, you would see incoherent dynamics here, coherent dynamics here. But what I'm talking about is even if your phase information between these eigenstates are lost, it's okay, as long as the eigenstates exist and you can have transitions between them that are fast. So that was my point. So, and a good example was this Ronaldo Samos paper, that if you make transitions between them, you can have exponential speed up, even if you lose the phase coherence between them.
So I didn't get why you assume that the quantum annealer can actually equilibrate for interesting problems. So basically I have two objections to this kind of notion. One is that this kind of notion that you have that this is more of like a PCA type of a compact representation of your data when you want to apply it to machine learning. First, it's not clear that the quantum superposition that you get in these eigenstates has enough support on interesting classical states that are for that classical problem that you can, in a sufficient time, you can sample from it. Because you're not going to measure in the computation energy eigenbases, you're measuring classical state. But it's not clear to me that this is going to equilibrate. How do you know that it's going to equilibrate, and how do you verify it?
So to answer you, the one way to get this kind of situation is to look at phase transition, near phase transition. Near phase transition are the case that you get extended eigenstates, and equilibration between the extended eigenstates are hard classically. And quantum machine, because it doesn't need to generate the eigenstate, it can equilibrate faster. And that's what Richard Harris is going to show you tomorrow. It's exactly measuring equilibration near extended eigenstates. But whether it has application for machine learning, I don't know. But even a little bit further towards complex problems, if quantum machine can equilibrate better, not 100%, better than classical competition, it can enhance quantum machine learning algorithms. So you don't need to come 100% equilibrium. You have to beat classical equilibration.
We're going to take one more question. Go ahead.
So when you talk about QMC, basically we're talking about path integral Monte Carlo.
Yes.
But I suppose if I use diffusion Monte Carlo in a problem like frustration, I wouldn't have those topological obstructions. So.
Yep. Diffusion Monte Carlo, open boundary quantum Monte Carlo don't give you a distribution. So I'm talking about getting a correct distribution. If you want to simulate, the topic was, can we simulate what quantum machine does? If you want to simulate, you have to get statistics and dynamics correctly. Open boundary quantum Monte Carlo, diffusion Monte Carlo doesn't give you a statistic correctly. So
We'll just do one more because it's getting late.
Thanks. No, I wanted to ask you, because have you taken into account that when you go from the the metallic side of the many body localization should be peculiar, at least in the sense that it is not diffusive, and after the state above the many body localization close to this transition may be extended but non-ergodic. And I would expect that then, as they are not ergodic and the dynamic is slow, when you go there, the dynamic is going to be slow, and your annealing is going to fail.
the dynamics will be slow, but the dynamics of quantum Monte Carlo will be completely stopped. So we are competing with quantum Monte Carlo. If quantum Monte Carlo wants to generate this dynamics, you have to have loops that extend along all the states that you have eigenstates extend. So as I showed you, the way quantum Monte Carlo simulate tunneling is by extending the loops. Now, if you have eigenstates that are extended, quantum Monte Carlo algorithm should have loops that are extended over many states. And this is very slow dynamics to equilibrate. So if you want to have a race against quantum Monte Carlo, that's what I mean. This is the regime you should look at. Quantum Monte Carlo cannot equilibrate in this state very quickly. Okay. Of course, everything will be slow. Near phase transition, all algorithms will be slow. But a quantum machine will be much faster than quantum Monte Carlo.
Okay. But then have you taken into account that the eigenstate above the many body localization transition would be extended but not ergodic? It wouldn't reach everywhere in your phase space.
It depends on how far you go. Yeah, I agree. But if it can extend to a stage that it can beat quantum Monte Carlo. But it wouldn't reach, yeah, I agree. If you want to reach all the states, you have to go very high. But
yes.
Yeah, I agree with that, yeah.
Okay, I'm going to call it quits because, we have to move on. So thank you very much.